welcome to VLSI Developers YouTube channel. In our last video, we have discussed about what is mean by Verilog HDL and different modeling styles of Verilog HDL. So today in this video, we are going to discuss what is the wire and register data type. See, what is the wire data type and register data type? Means I will give a basic idea about what is wire and what is register, and gate level modeling of all logic gates. All logic gates means including universal gates and special purpose gates also. So we are writing gate level modeling of all logic gates, and I will show you the simulation of gate level modeling of all logic gates by using Xilinx 13.2 tool. See, so our first topic is wire data type. So wire data type. Wire data type is nothing but it is a net type data type. Net type data type. So net type. Simply wire means, see, this is one gate and this is another gate. See, it's a B input, A and C input. So this is a G1 gate and this is a G2 gate. So in between these two gates, the output of this G1 gate is connected to input of this G2 gate. How it was connected? By means of one wire. Simply this is a wire data type. I am declaring that as W1. So it is a wire data type. So wire data type is used to connect two gates. One gate output and another gate input. So simply this is a wire data type. Next, register data type. Register data type means to store some values. We use register data type. Register, the word itself indicates we have already studied registers in our digital electronics subject. Register means storing of some data in binary form. So here this register data type is used to store some data. So register data type is used in case of behavioral modeling style. So I will explain these register data type in detail whenever we are going to discuss the behavioral modeling. So this is a basic idea what is mean by wire data type and what is mean by register data type. Yeah. Now we will discuss the logic gates and universal gates and special purpose gates. See, logic gates. See, first AND gate, two input AND gate. Here I am writing code for two input AND gate. See, A input and B input, and output of this gate is P, and another OR gate. See, two input OR gate, and input is A and B, and output is Q. See, this is NOT gate, single input single output. A and R is the output. You can write B also here, that's your wish. And next, NAND gate. These are universal gates. NAND gate and NOR gate. See, A and B, and this R and this S. And see, NOR gate. See, A and B are input and T is the output. See, this is XOR gate. See, A and B are input and U is the output. See, this is XNOR gate. Output V, input A and B. So see here, P is equals to A and B, and Q is equals to what this AR means A plus B, or we can write it as ARB, this as AB, and R is equals to A bar, and S is equals to AB whole bar, and T is equals to A plus B whole bar, and U is equals to AXR B, and V is equals to AXNOR B. We can write this also as AXR B whole complement. So these are all logic, these three are logic gates, and these two are universal gates, and these two are special purpose gates. So Now we will write gate level modeling code for all these gates. See. So in our Verilog language, we will start our writing of code from the module. So module we have discussed what is module means. Module is a fundamental block in this Verilog coding, or simply it is called as a function, particular function. So I am writing the code. First see module, and here I am writing logic gates. This is a module name, logic gates, and I am writing outputs p comma q comma r comma s comma t comma u comma v, and inputs a comma b. Here I am declaring the outputs. What is outputs and what are the inputs? Outputs are p comma q comma r comma s comma t comma u comma v, and inputs a comma b. See, now we are writing gate level modeling. For gate level modeling, for each gate we are having primitives. For AND gate, AND is a primitive. For OR gate, OR is a primitive. For NOT gate, NOT is a primitive. And for NAND gate, NAND is a primitive. And for NOR gate, NOR is a primitive. And for XOR gate, XOR is a primitive. And for XNOR gate, XNOR, XNOR is a primitive. So by using these primitives, we are writing the code. See, first AND gate, and I am giving the gate name as G1, and output of this AND gate is P comma A comma B. P is the output, A comma B are the input. Second, OR gate, or G2 of Q comma A comma B. And next, NOT gate, NOT G3 of R comma A. And NAND gate, NAND G4 of S comma A comma B. And NOR gate G5 of T comma A comma B. And XOR gate G6 of U comma A comma B. And XNOR gate XNOR G7 of V comma A comma B. So here we are completed these 7 gates, and at the end we have another keyword end module. So see guys, there is no space between this end and module. Totally it complete one word. So yeah, this is the gate level modeling code. So now I will write this code in Xilinx software, and I will show you the RTL schematic and the simulation waveform. So see guys, I am using Xilinx ISC 13.2 software. See, this is the user interface, and now I'm going to create the new project. See, this is the option for new project. Just I'm giving VLSI developers, and next I'm clicking next. And see here, don't change any options. It is by default Spartan 3 version of FPGA. Next, finish. We have created a project. Click this project and right click on that, and now you will add new source. For the new source, you see here the Verilog module. Click that Verilog module and write the name of this Verilog module as all logic gates, all underscore logic underscore gates. See, click next, and firstly we have declared outputs now. So first outputs are P comma Q comma R comma S comma T comma U comma V. See, these are the outputs, and inputs are A comma B. See, next, click next, finish. Yeah, so these are all we are getting inbuilt whenever we are creating a new Verilog file. Now we need to write the code from this line, 25th line. We need to write the code. So here we are using the inbuilt primitives. So first writing code for AND gate. and G1 of output is P comma A comma B. Next, for OR gate R G2 of Q comma A comma P. And for NOT gate, NOT G3 of R comma A. This is single input gate. And NAND gate now, NAND G4 of S comma A comma B. And NOR gate, NOR G5 of T comma A comma B. And after this XOR gate, XOR primitive and G6 of U comma A comma V. Sorry, B. And XNOR gate, XNOR G7 of V comma A comma B. See, it will getting by default end module. And now we need to save by using Control S. And see these three dots, this indicates this particular module is a top module like. And clicking on this, here we need to click this plus symbol beside the synthesis and clicking check syntax. It will display if any errors are there, otherwise it will give this green color tick mark. And now we are going to viewing the RTL schematic. See, so click OK. See, this is this is given in the format of integrated circuit. See, 2 inputs and this 7 outputs. See, this is the internal structure. It's AND gate, OR gate, inverter, giving inverters to these gates and generating NAND gate, NOR gate, and inside this we are having the XOR gate, and again giving complement to that we are getting XNOR gate. Yeah, we also see the technology schematic. See, this is technology schematic. In this technology schematic we are having the lookup tables. Yeah, we will discuss what is the lookup tables in our further video. See, by clicking this lookup table, I'm getting an equation for the gate and getting the diagram and getting the equation and getting the truth table and getting the K-map of this for the solving of this particular gate. See, in every lookup table, we are getting this type of truth tables, equations, and the schematic diagrams. Yeah. So this is the technology schematic, and now we will simulate this. By simulating this, we will verify the functionality of this particular circuit. And see, by right clicking on this circuit, we are getting the options. Now you should click to new source, and you will get this pop-up. And in this pop-up, you need to select the Verilog text feature, and you give some name. Just I'm giving all logic wave, and I'm clicking the next, and this is a selected model. If there are present multiple models, then you need to select for particular module and click next, finish. Yeah, it will automatically generate because it is an Xilinx version. And if you are using mentor graphic, means you need to write the this test bench code also. This is also called as a test bench. See here, see this is a 100 nanoseconds is a delay. Copy this one, Control C, and paste it here, Control V, and see this. So simply here I am writing the format of the truth table. Here we have two inputs. For the two inputs, we are having possible four outcomes like 0, 0, 0, 1, 1, 0, 1, 1. See here how I am writing here. Control V, Control V, Control V. See for A0, 0 and A0 B1 and A1 B0 and A1 and B is equals to 1. Yeah, just I have here I am framed the truth table. Now I am saving it one by using Control S and clicking this one. See here we are getting this option simulator, and you will in the simulation block and click this, you are getting the behavioral check syntax. Click on that. Yeah, it is right, there is no errors. Now click simulate behavioral model. You are getting a waveform. For viewing this clearly, yeah, press F6, function F6 in our laptops. In our PCs, directly click F6. Yeah, see, drag this and see, this is the, see, first P is the output for the AND gate. See, AND gate for A is equals to 0, 0, 0, A is equals to 0, 1, 0, A is equals to 1 0 0. For A is equals to 1 1 1. Yeah. Similarly, you can also verify for all logic gates, universal gates, and the special purpose gates. Yeah. This is about the waveform and this is about the functional simulation of the particular all logic gates. And now I will show you the synthesis report. In the synthesis report, you are going to get the mm, design parameters like how many lookup tables it have been used and see how many lookup tables and how many slices and number of input output blocks or input out buffers that have been used in that particular Spartan 3 version. C in available of 960 means it have used only 4 slices and available of 1924 input lookup tables means it have used only 7. In 66 IOBs it have used only 9. So it were occupied low area, less area. And see here the synthesis report, click on this. Yeah, go down, scroll. Here you are getting the delay. This is the delay 5 point, see 5.998 nanoseconds. So this was a lesser delay because 5.9 nanoseconds is smaller, very little delay. So these are the factors we have discussed today in our class, and in our next class we will discuss the data flow modeling of our logic gates, and after that we will discuss behavioral modeling. Okay, thank you. Please subscribe our channel and share to your friends. It is useful. Thank you. Bye.